Okay, good morning, everyone. I promised that I would put up some websites that we were talking about yesterday. So here at the top, you see the websites of IGEL, eRead, and our institute. I'm just going to show them to you in a minute as well. Then this one below, Statistics Hell, that was the one that I was talking about yesterday. Those of you who have tried it out already might have gotten a fright because it looks pretty scary, but it is the real website that I was talking about. It's not a joke. And then I also thought about this website of Matthew Jockers, who works at the Stanford Literary Lab. And he has written a really good book on how to use R when you work with text analysis. So if you have a project that is more sort of corpus linguistics minded, then that might be the right book for you. He also has a website where he has like a blog and all kinds of useful resources, so that might be a good website too. So I just want to show you some things on these websites. Let me see. So yeah, Statistics Hell, that's where you start. So this is Mr. Andy Field. You can see some of his publications, his work here, and here you have help for like different levels of where you're at in terms of your statistics knowledge. And he has with every one of these, just going to show that to you. With all of his topics, he has either handouts or YouTube videos. It's a really useful website. It looks a bit scary, it looks a bit strange, it looks a bit 90s, but it works. Okay, so this is Matthew Jockers' website. He even offers some online courses, I think, or this is the courses that he is giving at the Stanford Literary Lab, but I know that he also does some online courses, or he has developed an online course to sort of how you can figure out R, especially if you're working, as I said, with corpus linguistics methods. This is the best website out there, I think. Then I wanted to show you something on our IGEL website. Let me see where it is. Yes, membership. So I noticed that some of you already signed up this sheet in the kitchen. Here is our sort of PayPal, what do you call it, payment option that you could make use of. So it's very easy to find. For those of you who are wondering, why is the logo of IGEL in the shape of a hedgehog? That's because IGEL in German is a hedgehog. And it was originally, the society was originally founded in Germany. So it's Internationales Gesellschaft für empirische Literaturwissenschaften. So that's why it's a hedgehog. I've been asked this question so many times. This is so weird. Why is there a hedgehog around this? That's the reason. Okay, so this is the eRead website. Here you can find out more about the eRead project and how you might get involved. And I wanted to just point out, I didn't realize this, but Winfried Menninghaus told me yesterday, as of now, there are some PhD and postdoc positions available at our department. And I know that the closing date, it's kind of cutting it close because it's next week. If I had known about it before, I would have sent you an email before the training school, but maybe it's still time enough if you are thinking this might be a nice place to work. So that's the Max Planck website. Okay, then statistics. So this is an overview of what I'm going to talk about in this lecture. As I said, it's about descriptive and inferential statistics. I first will tell you a little bit about the difference between the two and when you need descriptive statistics, when you need inferential statistics, and then I will go further into detail into measures of tendency and dispersion, which are descriptive statistics, and the normal distribution. We will go more into detail on that. And then I will talk a little bit more about inferential tests and just tell you about two of them. Very simple ones. Probably a lot of you have done these before, at least heard about them, but I think it's good to start with the basics. I'm just going to tell you a little bit behind it, the theory, what exactly they can do for you. And then in the afternoon, my colleague Murali is going to give you the workshop with R, and he's really going to talk you through how you would do these kinds of analysis using R. Okay. So this is a slide you've seen already yesterday. but now I'll walk you through it. Descriptive and inferential statistics. So the difference between the two is that you would need descriptive statistics, the name already says it, to describe and summarize your data. But that is all that descriptives can do. It can only tell you something about your own sample. So for example, it could show you how many men and how many women there are in your sample. It could tell you what their mean scores are on reading pleasure, for example, for these groups. It could also even show you if these scores differ from one another. But it can't tell you anything about, is that difference significant, yes or no. That's why you need inferential statistics. We use inferential statistics to try to falsify our hypotheses about the relationships between our independent and our dependent variables. And they help us generalize beyond our own sample. So with inferential statistics, you could find out whether men scored differently on reading pleasure than women by coincidence, or whether it was an effect of your independent variable. In how far do their scores differ, and do these scores differ significantly? That's why you will need inferential statistics. Now, if you flip through newspapers or magazines or whatever, and you see sort of a nice graphs of, hey, this is how many percentage of people chose our product over that product or whatever. Usually what you see published in newspapers, it's descriptive statistics. It's not telling us actually a lot. Descriptive statistics are nice just to give you an idea of like what is in your sample, but it doesn't actually say anything about, well, is this significant that this percentage of people chose this product? Is it significant? Does it mean anything? No, it's just saying this percentage of people chose this product. So it kind of is misleading how far the media are always just sort of using descriptive statistics, but not really going into meaningful data. Okay. Descriptive statistics. We'll start there. So you have your data in. You have collected all of your data. You have entered everything into your statistical software program of your choice. Where do you start? Obviously, it's very tempting to immediately start running tests and trying out various tests to see if you can find something that's significant and that's meaningful. That's not what we do. You should start with descriptive statistics. It's relevant for the very first phase of your data analysis. It can help you look for mistakes in your data entry, especially if you have a stack of a paper. So people have responded with pen and paper questionnaires, and you have your stack of papers, and you're going to enter everything by hand in your statistical software program. Obviously, that's a lot of tiring work, and, well, we make mistakes. So you might have made a typo somewhere, and looking at your descriptive statistics might give you a hint to where you might have made mistakes during data entry. So it's always good to start there before you start running tests, because there might be mistakes still in your data set. You might need it to make your data file ready for inferential statistics. What happens a lot is that people sometimes skip questions in a questionnaire, especially if you have it on paper. Most of these online programs, they have options that you can force people to answer all of the questions before they can go on to the next page. But if you have a stack of paper, then sometimes they just miss entire pages or they miss a question, and you have what is called a missing value. And you need to instruct your statistical software program, this is where my participants skipped over the question. It's not that they answered, for example, if you have a scale in there from 0 to 7, it's not that they answered 0, it's that they didn't answer the question. You have to instruct your software program, this is a missing value. But it also helps you get a general picture of your sample, a general feeling of who is in the sample, how many males, how many females, what is their age range. So always start with descriptives. Like I said, it's used to summarize your data and to convert a large amount of data into kind of meaningful information in the sense that it can give you means and percentages. So let's talk about the kinds of descriptive statistics that we have. There are two things that mainly interest us when we are describing and summarizing our data. You want to sort of map the general tendency of all of your participants together, and you want to map the reactions of individual participants. For that, you need, on the one hand, measures of central tendency. On the other hand, you need measures of dispersion. And these two always go together. You can't say something useful about the one without the other, and vice versa. They complement each other, and together they give a more comprehensive view of your data. So first, measures of tendency. There are more measures of tendency than these ones, but these are the ones that are most often used. So you have the mean, the average. Everybody knows this. This is how you calculate the mean. You take all of the data points in your sample, you add them up, and you divide them by the number of data points in your sample. This one is the most often used, but it's not very informative on its own. Also, it's very sensitive to extreme values. So for example, in this data set, so let's say, no, that would be strange, but I can't come up with another example right now. Let's say these are ages of people in your sample. So you can see here that actually it's quite a young, like overall, the people in your sample are quite young. However, this one person of 104 years old is skewing your whole data set into one direction. So that's what I mean when I say it's sensitive to extreme values. Then you have the median. The median is the one value that always lies in the middle of the order. If you would order all of these values, because obviously when you ask people about their age, they will not be ordered in like a nice hierarchical way. You have somebody who is 2, somebody who's 104, somebody who's 28, like that. But if you would put them all, if you would line them up all nice hierarchically, then the median would be the one that lies in the middle of your order, which makes it less sensitive to outliers. So when you combine the mean and the median, you already know a little bit more about the tendency of your sample. Then there is the mode, and the mode is the most common value in your sample. So for example, here, you see there's 2 people of 2 years old in the sample, there's 3 people of 6 years old in the sample, and there's a 10-year-old and a 28-year-old. So then the 6-year-olds, that's the mode, because that's the most common value in your sample. This one is not very informative in small samples, only in large samples. So I'll give you an example. This one is an example of a study that I ran a little while ago on the effect of literary text features on the experience of absorption. So I included 2 different questions on reading habits in the questionnaire, because I assumed that a person's reading habits might be an intervening variable in this relationship between literary text features and absorption. So these are the 2 questions that I used. How many hours per week do you spend reading? And how many hours per week do you spend reading fiction for pleasure? Now, the participants could answer on a scale from 1 hour or less to 10 hours or more per week. And I used descriptive statistics in SPSS, because that's the program that I tend to use more often, to give me some insight into the general tendency of my data. So what you can see here is, first of all, the N over there. I think you all know what that means, or so that's the number of participants that's in your sample. So there were 224 people in the sample. Then you can see the mean, so the average score. And remember, this is both questions are on a scale from 1 to 10. So the mean here was around the 6, and here it was around 3. And the median is then the one that lies in the middle. So here you can see that the mean and median in both cases do not lie very far apart from each other, which seems to suggest that the mean is like the true average, that there are not a lot of outliers. However, the mode here provides us with some crucial information. So the data in answer to question 2, so how many hours per week do you spend reading fiction for pleasure, does seem to cluster around the mean, as the mode, so the most common value, is a 1. Whereas in the case of question 1, it doesn't really crowd around the mean, because the most common value is a 10. So if I then put 2 extra tables in here, which give you the frequency of like how many people chose this option. Sorry, that's in Dutch, I just realized, but you understand what it means. Less than 1 hour or more than 1 hour. So this is the number of people who chose like option 1 and so on for option 10. What you can see here is that for question 1, it's more spread out. Whereas for question 2, it's like more towards this side of the tendency. So this is just to illustrate that the more of these kinds of measures of central tendency you combine with one another, the more information you actually get about your data set. I think this is also a really nice example. That's also why I wanted to include it, of the fact that you need to think through how you ask your questions. Determine what you're interested in, use that one question or pilot test the questions beforehand, because when I did this, I didn't really think about it. I was under some time pressure. I had a group of students that I could use for an experiment, so I thought, okay, I'm going to set up an experiment real quick, and I put these questions in here, but I didn't really think through what I might sort of get back in terms of response. And actually, there's quite a difference between the two, and I was wondering for a long time, what do I do with this? Like, which question do I actually use now in my analysis? Do I want to use both questions as control variable or just one? Which one do I think relates more to my main research question? And I thought it was a nice illustration of even like the simplest change in your question might give you such a different answer, such a different response. So yeah, that's why I wanted to use that. If that is all clear up to now, then I'll go to the measures of dispersion. Sorry, this one. Yeah. Okay. So measures of dispersion. As I said, this shows you more about the tendency of the different participants in your sample, so how they differ from one another instead of how they respond in the same way. And adding these to the different measures of central tendency will allow you an even clearer view of your data. So again, there's more measures of dispersion than these ones, but these are the ones that are most commonly used. So you have the range, which is the difference between the lowest and the highest value in your sample. That's pretty self-explanatory. Then you have the standard deviation. The standard deviation is the mean deviation of the mean. So a low standard deviation, in other words, indicates a high level of agreement among your participants, whereas a high standard deviation would indicate a low level of agreement amongst your participants. And usually what you see most in research papers is that the mean and the standard deviation are the two measures of central tendency and dispersion that are used together to give some information to your readers about the descriptive statistics of your sample. Then you have variance, which is comparable to the standard deviation, but as I said, standard deviation is used more often. This is the variance within the dispersion. Okay, so yes.
Is it preferable then to have a low standard deviation in your results?
Yes, exactly. Is it preferable to have a low standard deviation in your result? Yes, that is, yeah. I'll give you an example. I'm going back to the example that I gave earlier, so the reading habits questions. Here, this is the same table that I showed you earlier, but now I added measures of dispersion to this. So now you can see by adding the standard deviation, variance, and also the minimum and maximum that you could score, that was scored here, that you could have figured out without the other two tables in the last slide, that the range was much bigger in question 1 than in question 2. So you can see here, the standard deviation here is much higher than it is here, which indicates that these participants did not agree too much with each other. That was spread out over the whole range of the points on the scale. Whereas here, the standard deviation is much smaller. The same goes for the variance. It's much higher in question 1 than in question 2. So in sum, measures of tendency and dispersion always go together. The mean and the standard deviation are the ones that are sort of used most often when reporting your results. Okay, now we get back to the normal distribution. These relations might even become more obvious in a visual representation of your data. The mean and standard deviation can tell you about the distribution of your data around the mean and whether your data is normally distributed. This here, like I said yesterday as well, is a normal distribution. So this line here is what we would call the normal distribution, and these bars here, they represent sort of the participants who chose the various options. This is a non-specified variable, but let's say it's their transportation scores. So you see that there's a scale from 0 to 8. A lot of people crowd around the mean of this scale. There's some people, but less and less so, that score higher on transportation, and some people that score pretty low on transportation. We call this also a bell curve for obvious reasons. Normal distribution is what we call an ideal distribution, one that you do not see often in small samples, I'm sorry to say. One we do not see very often in empirical literary studies because we use small samples. Because the more observations that you use, the greater the chance you have of a normal distribution. That's just basic chance calculation. So some good examples of really good, robust normal distributions are, for example, weight, length, and IQ. Like if you look across the whole population, like what would be an average length, it would be around, I don't know, 1 meter and 70 centimeters or something. And then there's a couple of those people that are like 2 meters and 20 centimeters long. And there's a couple of people who are 1 meter, 40 centimeters short. That's not really a nice way to put it, but you get the picture. Okay. We will get back to the normal distribution a little bit later in this lecture because the normal distribution is of crucial importance once we get at the moment where we're going to decide which statistical tests we need. Because for some statistical tests, this is an assumption that your data has to meet before you can run a certain test. So your data has to be normally distributed because otherwise you're not allowed to use certain statistical tests. Okay. Another way of visualizing your descriptive statistics would be with a box plot. You see these a lot in research papers as well. The box plot gives you summarized values. So if you look here, you see here in the middle is the median of your sample. This bar sort of represents the 50% of your participants that crowd around closest to the mean. Then these little whiskers is what we call them. They show sort of the 57th and the 25th percentile. And everything that is included sort of between these whiskers on the upside and the lower side indicates the range of your data points. Then you also see these little stars and little circles, and those sort of indicate your outliers or your extreme values. So imagine, for example, that you conduct an experiment with a group of students that you are currently teaching, and you're making a box plot of their age range, just to see what their age is. The median will probably lie around 21 if you're teaching a bachelor's course. Then the square sort of around the median will indicate that 50% of your sample crowd around that mean will be students ranging from 20 to 22-year-old. Then there are some students that are a little younger, a little older than the average students, so they would fall sort of in the 25th and the 75th percentile, so the 19-year-olds, 23-year-olds. But there's a few of them every now and then that go back to college after they have retired, for example. So you might have somebody in there from 67-year-old. Such a person would be an extreme value in this case, and it would be indicated by a little star or a little circle. And I think it's really good to use a box plot is very helpful in this sense to, like I said earlier, to see whether you, for example, made mistakes with some data entry. So these outliers sometimes, well, you have cases in which you have 76-year-olds in your sample. It's worthwhile, though, to examine these outliers more closely. It might be that you, for example, made a typo when you entered your data, and instead of somebody that was 55 years old, you meant to type 25-year-old, for example. Because an outlier obviously affects what the mean of your data distribution is, sometimes in rather dramatic ways, it may be worth to investigate them to see whether you made any mistakes. If you did correct a mistake, might make a difference between your data being normally distributed or not normally distributed, and that, as I said, has effects on what kind of tests that you can use. So box plots are really helpful with this kind of investigative work. Let me see. Yeah. Okay, so when the median, now here in this example, it lies pretty much in the middle of the little box. when it doesn't lie exactly in the middle of your box, you know that your data is skewed in one direction, which is another way of saying that the data is not normally distributed. The bell curve would then sway in either the left direction if the median is below the mean, or to the right if the median is above the mean, like so. I think I have everything here. Yes. So I'll just give you one example of a box plot with the data from the example study. So what I did here is I divided the participants in two groups, one that read from the booklet, one that read from the iPad, and then here I plotted the total score that they had on transportation. This is just to give you an idea. So what you see here is, okay, so what do you see here? Let's see if you are awake yet. What do we see here? Anybody want to venture a guess? What can we tell from this box plot? The iPad, yes. So that's a good first observation. So the iPad would be a normal distribution. However, in this group, the data doesn't seem to be normally distributed, or not as much so as in this group, because the median here doesn't lie exactly in the middle of the box. What else? The range is different, yes. So, for example, in the booklet condition, there seems to be much less agreement among participants about how absorbed they were. So you see here the whiskers range all the way from the 4 to the 1, whereas here they seem to be more in agreement about how transported they were when reading from an iPad. What else? Which group scored higher on transportation? Sorry, I didn't hear anybody respond. Booklet, yes. So you can see that because this line is higher than this line, obviously the box is also a little bit higher. It's not a big difference. We'll see later on that I run a t-test on this specific example, and then we'll see whether this difference would be significant enough to say that there's really a difference between these two groups. I have to admit, though, that I didn't split it up again in the other two conditions. So here, all of the people who read the instructions with this is a fiction text or this is a non-fiction text, they were put together. So it's just a difference between people who read from a booklet, people who read from an iPad. Was this clear so far? Yeah? Okay. So then, after you have got a feel for your data, we've described your sample, you have corrected any mistakes that you might have made when you entered your data, you have told SPSS or R where the missing values are in your sample, it's still not time to start randomly trying out tests. You need to determine beforehand which test that you need to answer your specific questions. This will help you at least make a little bit of a guess in the right direction. You have two types of tests within inferential statistics. You have tests that measure the correspondence between variables, and you have tests that measure the difference between variables. So examples of correspondence tests would be correlations and regressions. I highlighted the correlation because that's the one that we're going to talk about today. And then under difference testing, you see the t-test and, for example, the analysis of variance or ANOVA. Again, I'm going to look at the t-test. But if you've mastered the correlation and the t-test, basically the regression and the analysis of variance are just sort of more advanced forms of the correlation and the t-tests. So I'm sure that once you've mastered sort of these basic tests, it's fairly easy to go on for a little bit more complicated. Okay. Correlations, like I said, they represent a correspondence between two variables. A correspondence or a correlation is indicated by an R, again, always written cursively, or a correlation coefficient is what we call it as well, and it's represented by a number between -1 and 1. A correlation coefficient between 0 and 1 indicates a positive correlation between the two variables that you're measuring. And it means that the values of the two variables move in the same direction. I will give an example of this on the next slide. Then correlation coefficient between 0 and -1 indicates a negative correlation, and in that case the values of the variables will move in opposite directions of each other. When the correlation coefficient is 0, it indicates that there is absolutely no relation between the variables whatsoever. So, for an example, visualizations always help with these kinds of things. And it helps really well to explain the difference between positive and negative correlations. For this, you can use, when you're doing correlations, you can use a scatter plot. So you have to think that all of the dots that you see here, those are sort of the singular observations in your data set, and the line indicates the direction of the correlation between the two variables. So, for example, this would be a positive correlation going from the left lower corner to the right upper corner. Here in the example, for example, you have one variable that measures the hours that somebody spent revising for an exam. And then the other variable would be their exam result in the end. You can see here that the more hours people revise, the higher their exam scores. That's what the line is telling you. This is an example of a negative correlation. So one variable is the number of flu shots or flu jabs that have been given to a certain population. And then the other variable is the number of people in that sample that have the flu. You can see that the less flu jabs are given, the more people with flu in your sample. Words of warning though. A correlation only indicates a correspondence between two variables. It does not, however, tell anything about the nature of the relationship between these variables. So you cannot infer a causal relationship between variables based on a correlation. So like in the examples, for example, the number of hours that you revised did not cause the better results. So it is likely, of course, that it might have an effect. You just cannot conclude it based on a correlation. There might have been other variables in your data set or outside of your experiment that have influenced the exam results. So correlations just only tell you whether or not the two variables correspond to each other, yes or no. And I'm stressing this because I have seen people make the mistakes, even in published papers, that they sort of stress that, well, I found a correlation between this and that variable, so this caused that. But that's not done. That's not allowed. So be careful with your conclusions that you base on correlations that you run. And always use, that would be a good tip, I think, always use comparable research when you are interpreting your findings. So of course, when you find such a strong correlation between hours of revising and exam results, you can say, well, I found a high correlation between the two. And this suggests that the two are related in such a way that this might lead to that. And I have some other research that I can base that sort of conclusion on. However, in order to be sure, we would need to do a test to see whether that's actually the case. So an example from the example study, I ran a correlation on two of the variables in the iPad study. So I found a variable in there that said number of university literature courses that the participants partake in, and then their total transportation score, because I thought those might relate to each other. So what we see here again, the N again indicates that there's 145 people in this particular sample. Then you can see this number here, that's the actual correlation coefficient, so it's 0.132. And the sig here, that always indicates the p-value of a certain test, so the probability level. You can see here, what can we see here? Yes? It's not significant, yes. When would it have been significant? Yes, below 0.05, yes. So I thought, this doesn't really tell me anything at this point. Okay, the only thing that it tells me is that it's a positive correlation, because if it would have been a negative correlation, there would be a minus sign here. But I thought I'd draw up a scatter plot anyway, just to see how it would look. This is how it looks. You can see here that this is the number of university courses that they took from 0 to 5, and there's the total transportation score. The line does sort of have a tilt a little bit higher on the right side, but it's not very impressive. This is here how you would report a correlation in a research paper. So you would start with the correlation coefficient, again, cursively, and then a comma, p-value cursively. And in this case, because it's not significant, you would use the is sign. If it would be significant, you would use the it is lower than sign. Okay. Was that all clear? If that was clear, then we're going to go on to difference testing. So, inferential statistics. Just to refresh your memory, inferential statistics, and then the part where you're testing for differences between the variables and not correspondence between the variables, is used to determine whether your independent variable had an effect on your dependent variable. So, for example, I need some water. For example, if you wonder about the effect of digital devices on levels of transportation, you turn this into a hypothesis first that is about a difference between groups, like we talked about yesterday. One group you ask to read from an iPad, and the other group you ask to read from paper. They then fill out the same transportation questionnaire, and you compare their scores to one another to determine whether there is a difference. If there is a difference and you have controlled for possible intervening variables, and the difference is significant, you can conclude that reading from a digital device, which would be your independent variable, has an effect on transportation, which would be your dependent variable. Now, there's a whole range of different tests that you can use to test the significance of that difference between groups. For example, you can compare different groups of people in a between subjects design, so you would compare two different groups of people to one another. You might also be interested in differences between different times that the same group of people does something, reads a text, does a certain task, which would be the within subjects design. The choice for the right test depends on what your data looks like. For some tests, there are certain assumptions that your data needs to adhere to. Now, we have a really handy flowchart. It's on page 231 of the Scientific Methods for the Humanities, which can help you make the decision for which test to use. So I'll just go briefly through the different assumptions or decision moments in the flowchart that you will have to go through. So these are the 4 criteria that you need to judge your data on to be able to make the right choice for the right tests. You will start with, is your data normally distributed? Like I said, this is a really important thing for you to be able to use more advanced statistical tests. Then you need to sort of make sure that you know whether you are comparing within subjects or you're comparing between subjects. Then you need to know for sure that you know what the measurement levels of your variables are. And the last one, you need to know how many independent and how many dependent variables you have in your design. So these are the 4 things that you sort of need to have down before you even start collecting your data, because they will be very important later on. Okay, so just to show you in the flowchart, the most important one is your data normally distributed? If yes, you can use parametric tests. Parametric tests are the more advanced tests in there. You can include multiple dependent, multiple independent variables there. You can take covariates, so possible intervening variables, into account in your statistical test. And these kinds of things are not really doable on this side, where you have the non-parametric tests. So if you find that your data is not normally distributed, it's not the end of the story. You can still test for differences and whether the difference between groups is significant. However, you have to find different ways to take all of your sort of control variables and stuff into account, because these tests are less advanced. So that is why it's super important that your data is normally distributed. And that's also why I would always say, try to go for more participants than you need instead of trying to work with little groups, because the more participants you do have in your sample, the higher the chances of a normal distribution. Okay, that normal distribution again. I just told you all of this. Okay, good. How do you figure out whether your data is normally distributed? So you can look at a bar chart, one of those visualizations that I showed you earlier. You could use that. You also, if that is not super clear to you, you can also use an objective test, the Kolmogorov-Smirnov test. That's quite a mouthful. I just call it the Smirnov test. Be done with it. This test compares the scores in your data set to a hypothetical data set that would have the same means and same standard deviations as your data set. And in that hypothetical data set, the data is normally distributed. So when you would look at the outcome of the Smirnov test, you would actually want the outcome to be non-significant. Because when the test is not significant, the distribution of your data does not differ from a normal distribution, and thus you can assume that your data is normally distributed. Again, kind of roundabout, but so what you have to remember is the outcome of the Smirnov test needs to be non-significant. If you have a non-significant outcome, you can use parametric tests. That's basically all you need to remember. And I'm hoping, I asked Murali for this as well, I'm hoping that he's going to show you how to do a Smirnov test this afternoon, because that's basically the most important test in the book. If you know how to do that test, then in any case, you always know for certain whether or not you can use parametric tests or not. Okay. Today we are only going to look at the left side of the flowchart. So I'm just going to assume that the data is normally distributed because that's where the cool tests are, on the left side. Like I said, the non-parametric tests basically do the same thing as the parametric tests. They test whether there is a difference between groups, whether that difference is significant, but they are less advanced. So for example, you are not allowed to include, or you're not even, it's not even possible to include covariates in your tests. Today I will just focus on the t-tests, which is the most simple test of the parametric tests. Once you've mastered that one, the analysis of variance or the general linear model, who are over there on the left side, will be easy to do as well. Because basically, t-test you do when you have one independent variable and one dependent variable. That's when you arrive at the t-test. But if you have more than one independent variable, or if you have more than one dependent variable in there, you need to go to either the analysis of variance or the general linear model. But it's the same as the t-test. It's just trying more things at the same time. You could even do, for example, if you have more than one independent variable, more than one dependent variable, you could test them all separately with like a whole bunch of t-tests. You could do that, but it's more convenient to do it with a test like that. And apart from that, it gives you a clearer idea of how the variables are related, because you take all of the variables into account at the same time. Okay, t-test. The most important assumption here, like I said, is that your data needs to be normally distributed, and apart from that, your measurement level should at least be interval. So Berenike told you yesterday about different measurement levels. Interval is that when you use scales, for example, when you use Likert scales, so from 1 to 7 or 1 to 5, doesn't really matter what the range of the scale is. If it's a scale, it's interval, and you can use a t-test. There are two different t-tests to measure differences between groups. You have an independent samples t-test, which is basically between subject design, because it's two independent of each other groups of people that you're testing, and you have a paired samples t-test for within subject design. I'm going to do a independent samples t-test, or I did an independent samples t-test already, because I now looked up whether the difference between transportation scores for those two groups, the booklet readers and the iPad readers, whether that was significant or not. Now Murali will explain you how to run this test using R in the afternoon. I ran it using SPSS, and here you can see the output. The output of R will look different, but it will basically have all the same things in there. So first what you will get is a table noting your descriptive statistics. So can anybody tell me how many participants there are in the two different groups? Louder. Yes, 73 and 72. So 73 in the booklet condition, 72 in the iPad condition. We can find that under the N. Then, which group scored higher according to the descriptive statistics table. Yes, the booklet. So you see here 2.4 and 2.2. This was on a scale from 1 to 4, 0 to 4, something like that. So it's not a really big difference between the two, you can already see. The standard deviation tells you a little bit that, okay, they score higher, but they also agree less with each other. It's more sort of spread out than this group. Okay, then we're going to go to the test statistics, the table below. Oh yeah, let me just tell you the standard error on the right, what that is as well. The standard error indicates the sample standard deviation divided by the square root of the sample size. This translates to, because that was just a bunch of mathematical stuff, it translates to that whenever you see a small standard error, this tells you that most pairs of samples from a population will have very similar means. So if you would compare it to another sample, you would find very similar means. A large standard error tells you that the sample means can deviate quite a lot from the population mean, and so differences between pairs of samples can be quite large by chance alone. And they are only, like when I say small and large, it's only meaningful within this table. So you want to know which one has the larger one, which one has the smaller one. So in any case, we can see at a glance that people who read from paper were more transported. We do not know yet whether they felt significantly more transported. And for that, we need the lower table. This table, as you can see, start with the Levene's test for equality of variances. That is one presupposition for the t-test, that the variances of the two groups under consideration are roughly equal. If this assumption is not met, adjustments can be made. So again, with the Levene's test, the same as for the Smirnov test, you want it to be non-significant. So if the Levene's test is significant, so if the p-value is below 0.05, it means that the variances of the two groups are not equal and the assumption would be violated. No panic at that point, because then what you would do is basically you would read the output of the line down here. Equal variance is not assumed. You would just read that output. If it is not significant, like so here the equal variances can be assumed. So we can read from the top line of the table. The most important thing to us in this particular table is the significance. So the p-value, the probability level. Who can tell me whether or not the difference between the two groups was significant? Yes, I would say that based on this as well. The significance is 0.058. So it's not technically significant, but it shows a tendency towards significance. Apart from our significance, our p-value, we also need to write down our t-value, so the actual statistics, which you can find under t here. We need to use the one that's on the top line, and you need to write down the degrees of freedom, the df. Yes, so that's right next to the t. And with that, your readers have everything that they need to check whether you have drawn the right conclusions or not. Some journals nowadays also ask for confidence intervals, and SPSS immediately gives them to you as well. Not sure whether R does, but Murali will probably tell us everything about that this afternoon. So the most important are means, standard deviations, p-values, t-values, and the degrees of freedom. Those are the ones that you need to report on. A little bit about degrees of freedom. They indicate the amount of observations within your sample that you can vary to reach a given mean. So to calculate degrees of freedom, basically you take the number of participants minus 1. This would be the way in which you would report this result. There's almost a significant difference between iPad readers, and then you give the mean of that group with the standard deviation of that group, and paper readers, again, mean and standard deviation, in their levels of transportation. You will give the t-statistics, the degrees of freedom, and then the p-value. And you tell that in this case, it was a two-tailed test because you didn't have hypotheses about the direction of the difference. And then usually I would add a line as well, just saying it in plain English. Paper readers feel more transported than iPad readers. Okay. That was it. So that was not that scary. Does anybody have any questions at this point?